Let f be a function from the open interval 0 to 1 to the real numbers, defined as f of x equals square root of n, if x belongs to the interval from 1 over n plus 1 to 1 over n, where n is a natural number. Let g be a function from the open interval 0 to 1 to the real numbers, such that the integral from x squared to x of square root of 1 minus t over t dt is less than g of x, which is less than 2 times square root of x for all x in the open interval 0 to 1. Then find the limit as x approaches 0 of f of x times g of x. The options are: a does not exist, b is equal to 1, c is equal to 2, d is equal to 3. The answer is option C. We need to solve a one-sided limit to get the answer. Otherwise, the limit, as x approaches 0, doesn't exist since it's not in the domain. F of x equals the square root of the greatest integer less than or equal to 1 over x, minus 1, where the floor symbol denotes the greatest integer function. The limit as x approaches 0 from the right of the integral from x squared to x of square root of 1 minus t over t dt times the square root of floor of 1 over x minus 1 is less than or equal to the limit of f of x times g of x, which is less than or equal to the limit of the square root of floor of 1 over x minus 1 times 2 times square root of x. Now the limit as x approaches 0 from the right of the square root of floor of 1 over x minus 1 times 2 times square root of x equals the limit of 2 times square root of x times square root of floor of 1 over x, assuming 1 over x is not an integer. This equals the limit as x approaches 0 from the right of 2 times square root of x times the quantity 1 over x minus the fractional part of 1 over x, which equals 2. This equals the limit as x approaches 0 from the right of 2 times square root of x times 1 over x, which equals 2, again assuming 1 over x is not an integer. The limit as x approaches 0 from the right of the integral from x squared to x of square root of 1 minus t over t dt times the square root of 1 minus x times the fractional part of 1 over x equals this integral times the square root term, all divided by the square root of x. The limit as x approaches 0 from the right of the integral from x squared to x divided by square root of x equals the limit of the square root of 1 minus x over x minus 2x times the square root of 1 minus x squared over x squared, all divided by 1 over 2 times square root of x. This simplifies to the limit as x approaches 0 from the right of 2 times square root of 1 minus x minus 4 times square root of x times square root of 1 minus x squared, which equals 2. Similarly, for the case when 1 over x is an integer, the result is also equal to 2. Let a 1, a 2, a 3, and so on be an arithmetic progression with a 1 equals 7 and common difference 8. Let t1, t2, t3, and so on be a sequence such that t1 equals 3 and tn plus 1 minus tn equals a n for n greater than or equal to 1. Then, which of the following is or are true? A. t20 equals 1604. B. The sum of tk from k equals 1 to 20 is 10,510. C. t30 equals 3,454. D. The sum of tk from k equals 1 to 30 is 35,610. First, let's find the general term for the arithmetic progression. The first term is 7, and the common difference is 8. The formula for the nth term is a n equals a 1 plus n minus 1 times d, which simplifies to 8n minus 1. Next, we'll use the given recurrence relation. Tn plus 1 minus tn equals a n. This is a classic setup for a telescoping sum. If we sum this relation from k equals 1 to n minus 1, the left side will be the sum of tk plus 1 minus tk, and the right side will be the sum of a k. The sum on the left collapses, leaving us with tn minus t1 equals the sum of a k from k equals 1 to n minus 1. Let's calculate the sum of the first n minus 1 terms of our AP. Using the sum formula, it simplifies to n minus 1 times 4n minus 3, Substituting this back, we get Tn equals T1 plus this sum. Since T1 is 3, Tn simplifies to 4n squared minus 7n plus 6. This is our general formula for Tn. Now let's check the options. For T20, we plug in n equals 20 into our formula. This gives 4 times 20 squared minus 7 times 20 plus 6, which equals 1,466. Therefore, option A is false. For T30, wait, let me reevaluate my approach. The solution in the image calculates Tn plus 1. Let's follow that, as it might be simpler and avoid errors. Let's find a formula for Tn plus 1 instead. Tn plus 1 minus T1 equals the sum of a k from 1 to n. The sum of the first n terms of the AP is n times the quantity 4n plus 3. So Tn plus 1 equals T1 plus this sum, which is 3 plus 4n squared plus 3n. Let's use this formula. To check option C, we want to find T30. We must set n equal to 29 in our formula for Tn plus 1. This gives 3 plus 4 times 29 squared plus 3 times 29, which equals 3,454. Option C is true. Now let's check the sum in option B. The sum of Tk from 1 to 20 can be written as T1 plus the sum of Tk from 2 to 20. We can reindex the sum using our formula for Tn plus 1. This becomes T1 plus the sum of Tn plus 1 from n equals 1 to 19. Substituting our formula, we get 3 plus the sum of 3 plus 4n squared plus 3n. We evaluate this by splitting the sum. We have 3 plus 3 times 19 plus 4 times the sum of n squared plus 3 times the sum of n. Using the standard formulas for these sums, this equals 60 plus 9,880 plus 570, which totals 10,510. So, option B is also true. Performing a similar, longer calculation for the sum up to 30 terms gives a result of 35,615. Therefore, option D is false. So, the correct statements are B and C. Consider the equation. The integral from 1 to e of the square root of the natural log of x, divided by x times the quantity, a minus the natural log of x to the power of 3/2 squared dx equals 1. Is an element of the set negative infinity to 0, union 1 to infinity. Which of the following statements is or are true? A. No, a satisfies the above equation. B. An integer, a satisfies the above equation. C. An irrational number, a satisfies the above equation. D. More than one, a satisfy the above equation. We are given an integral equation. Let's start by analyzing the integral part. To solve this integral, we'll use the substitution method. Let's set t equal to the expression in the denominator, which is a minus the natural log of x to the power of 3/2. Now we differentiate t. With respect to x, this gives us dt equals negative 3/2 times the square root of the natural log of x times 1 over x dx. By rearranging this equation, we can express the numerator of our original integral in terms of dt. The square root of the natural log of x over x dx is equal to negative 2/3 dt. Next, we need to change the limits of integration from x values to t values. For the lower limit, when x is 1, the natural log of 1 is 0, so t is equal to a. For the upper limit, when x is e, the natural log of e is 1, so t is equal to a minus 1. Now we substitute our new variable, limits, and differential into the integral. It becomes the integral from a to a minus 1 of 1 over t squared times negative 2/3 dt, all equal to 1. We can pull the constant negative 2/3 out of the integral. The integral of t to the power of negative 2 is negative 1 over t, so we evaluate this from a to a minus 1. Applying the fundamental theorem of calculus, we get 2/3 times the quantity 1 over a minus 1 over a equals 1. Combining the fractions inside the parenthesis gives us 2 divided by 3 times a minus 1 equals 1. Rearranging the equation, we get 3, a squared minus 3, a minus 2 equals 0. We solve this for a using the quadratic formula, which gives us a equals 3 plus or minus the square root of 33, all divided by 6. This gives us 2 distinct solutions for a. Since the square root of 33 is irrational, both of our solutions are irrational. A quick check confirms that both values lie within the allowed domain for a. Therefore, we have found 2 distinct irrational solutions. This means that statement C, an irrational number satisfies the equation, is true, and statement D, more than one a satisfy the equation, is also true. Let L1, L2, up to L100 be consecutive terms of an arithmetic progression with a common difference D1. And let W1, W2, up to W100 be consecutive terms of another arithmetic progression with a common difference D2, where D1 times D2 equals 10. For each I from 1 to 100, let Ri be a rectangle with length Li, width Wi, and area I if a 51 minus a 50 equals 1000. Then find the value of a 100 minus a 90. First, let's define our arithmetic progressions. For the sequence of lengths, let the first term be a, and the common difference be D1. Similarly, for the sequence of widths, let the first term be b, and the common difference be D2. The formula for the nth term of these progressions are Ln equals a plus n minus 1 times D1, and Wn equals b plus n minus 1 times D2. Now, let's use the given information. A 51 minus a 50 equals 1000. This means L51 times W51 minus L50 times W50 equals 1000. Substituting the general term formulas, we get a plus 50 D1 times B plus 50 D2 minus a plus 49 D1 times B plus 49 D2 equals 1000. Let's expand the products. This gives us a b plus 50 a d2 plus 50b d1 plus 2500 d1 d2 minus the quantity a b plus 49 a d2 plus 49b d1 plus 2401 d1 d2 equals 1000. After subtracting and simplifying the terms, we are left with a d2 plus b d1 plus 99 d1 d2 equals 1000. The question states that d1 times d2 is 10. Substituting this in, we get a d2 plus b d1 plus 99 times 10 equals 1000. This simplifies to a d2 plus b d1 equals 10. We'll label this as equation 1 for later use. Now we move on to what we need to find. A 100 minus a 90, which is equal to L100 times W100 minus L90 times W90. Again, we substitute the formulas for the terms. A plus 99 D1 times B plus 99 D2 minus a plus 89 D1 times B plus 89 D2. Expanding and simplifying this expression directly, we get 10 a D2 plus 10B D1 plus 99 squared minus 89 squared, all times D1 D2. We can factor out a 10 from the first 2 terms. For the third term, we use the difference of squares formula. A squared minus b squared equals a minus b times a plus b. This simplifies to 10 times the quantity a d2 plus b d1, plus 10 times 188 times d1 d2. Now it's time to substitute our known values. From equation 1, a d2 plus b d1 is 10, and we are given that d1 d2 is 10. So we have 10 times 10, plus 1,880 times 10. This equals 100 plus 18,800, which gives us the final answer of 18,900. Let S be the reflection of a point Q with respect to a plane. The plane is given by the vector equation r equals negative t plus p, I hat plus t j hat plus 1 plus p k hat, where t and p are real parameters. The position vector of q is 10 I hat plus 15 j hat plus 20 k hat, and the position vector of its reflection s is alpha I hat plus beta j hat plus gamma k hat. We need to determine which of the given options are true. First, we need to find the standard Cartesian equation of the plane from its given vector form. The given vector equation can be rewritten by grouping the terms with parameters t and p. This gives r vector equals k hat plus t times negative I hat plus j hat plus p times negative I hat plus k hat. This form tells us that the plane passes through the point 0, 0, 1, and is parallel to the vectors negative I hat plus j hat and negative I hat plus k hat. The normal vector to the plane is perpendicular to both of these vectors, so we can find it by taking their cross product, which results in I hat plus j hat plus k hat. Using the point normal form, the equation of the plane is x plus y plus z minus 1 equals 0. Now we can find the coordinates of the reflection s of the point q, which is 10, 15, 20 in this plane. We apply the standard formula for the reflection of a point across a plane. Plugging in the values, the expression simplifies to negative 2 times 44 divided by 3, which is negative 88 over 3. From this equality, we can solve for each coordinate. Alpha equals 10 minus 88 over 3, which is negative 58 over 3. Beta equals 15 minus 88 over 3, which is negative 43 over 3. And gamma equals 20 minus 88 over 3, which is negative 28 over 3. Now let's check the options. Option A, 3 times the sum of alpha and beta is 3 times negative 101 over 3, which equals negative 101. This is correct. Option B, 3 times the sum of beta and gamma is 3 times negative 71 over 3, which equals negative 71. This is correct. Option C, 3 times the sum of gamma and alpha is 3 times negative 86 over 3, which equals negative 86. This is also correct. Option D, 3 times the sum of alpha, beta, and gamma is negative 129, which is not equal to negative 121. This is incorrect. Therefore, the correct options are A, B, and C. Let P1 and P2 be two planes given by the equations P1, 10x plus 15y plus 12z minus 60 equals 0, and P2, negative 2x plus 5y plus 4z minus 20 equals 0. Which of the following straight lines can be an edge of a tetrahedron that has two of its faces on these planes? For a line to be an edge of the tetrahedron, it must either connect a point on plane P1 to a point on plane P2, or it must lie completely within one of the planes. This means a valid line will intersect the planes at two different points, or be contained entirely in one of them. We will check each option by parameterizing the line and substituting it into the plane equations. For option A, a general point on the line is 1, 1, 1 plus 5 lambda. Plugging this into the equations for P1 and P2 gives us 60 lambda minus 23 equals 0 and 20 lambda minus 13 equals 0. These equations yield two distinct values for lambda, meaning the line intersects the planes at two different points. So, there is a possible edge. For option B, a general point is 6 minus 5 lambda, 2 lambda, 3 lambda. Substituting this into P1 gives 16 lambda equals 0, so lambda is 0. Substituting into P2 gives 32 lambda minus 32 equals 0, so lambda is 1. Since we found two distinct values for lambda, this line also intersects the planes at two different points, so B is a possible edge. For option C, a general point is negative 2 lambda, 4 plus 5 lambda, 4 lambda. Plugging this into P1 gives 103 lambda equals 0. Plugging into P2 gives 45 lambda equals 0. Both equations are only satisfied when lambda is 0. This means the line intersects both planes at a single point, so it cannot form an edge of non-zero length. Option C is incorrect. For option D, a general point is lambda, 4 minus 2 lambda, 3 lambda. Let's substitute this into the equation for plane P2. After expanding, the equation simplifies to 0 equals 0. This is an identity, which means it's true for any value of lambda. This tells us that the entire line lies on plane P2. Since an edge of a tetrahedron must lie on one of its faces, this is a valid configuration. So, D is a possible edge. Therefore, the lines described in options A, B, and D can all be edges of the tetrahedron. Find the number of 4-digit integers in the closed interval from 2022 to 4482, formed by using the digits 0, 2, 3, 4, 6, and 7. We need to count the integers in the interval from 2022 to 4482 using the available digits. We will do this by considering cases based on the first digit of the number. Case 1, numbers that start with the digit 2. For numbers of the form 202 blank to be greater than or equal to 2022, the last digit can be 2, 3, 4, 6, or 7. This gives us 5 numbers. For numbers of the form 20 blank blank, if the third digit is from the set 3, 4, 6, 7, which is 4 options, the last digit can be any of the 6 available digits. This gives 4 times 6, which is 24 numbers. For numbers of the form 2 blank blank blank, if the second digit is from the set 2, 3, 4, 6, 7, which is 5 options, the last 2 digits can each be any of the 6 available digits. This gives 5 times 6 times 6, which is 180 numbers. So, the total count of numbers starting with 2 is 5 plus 24 plus 180, which equals 209. Case 2, numbers that start with the digit 3. For numbers of the form 3 blank blank blank, the other 3 digits can be any of the 6 available digits. This gives 6 times 6 times 6, which is 216 numbers. Case 3, numbers that start with the digit 4. Remember, these numbers must be less than or equal to 4482. If the second digit is from the set 0, 2, 3, which is 3 options, the last 2 digits can be any of the 6 available digits. This gives 3 times 6 times 6, which is 108 numbers. If the second digit is 4, the number is of the form 4, 4 blank blank. The third and fourth digits can be any of the 6 available digits, giving 6 times 6, or 36 numbers. This is valid since the largest number we can form, 4477, is less than 4482. The total count of numbers starting with 4 is 108 plus 36, which equals 144. To get the final answer, we sum the totals from all 3 cases. 209 from case 1, plus 216 from case 2, plus 144 from case 3. Adding these up, we get 209 plus 216 plus 144, which equals 569. Let z-bar denote the complex conjugate of a complex number z, and let I equal the square root of -1. In the set of complex numbers, the number of distinct roots of the equation z-bar minus z squared equals I times the quantity z-bar plus z squared is blank. First, let's write down the given equation. Z-bar minus z squared equals I times the quantity z-bar plus z squared. Now, we'll rearrange the terms to group z-bar and z squared. This gives us z-bar minus I times, z-bar equals z squared plus I times z squared. Factoring out the common terms, we have z-bar times the quantity 1 minus I equals z squared times the quantity 1 plus I. The next step is to take the modulus of both sides of the equation. The modulus of z bar times 1 minus I equals the modulus of z squared times 1 plus I. Using the properties that the modulus of z bar is equal to the modulus of z, and the modulus of a product is the product of the moduli, we get modulus of z bar times modulus of 1 minus I equals modulus of z squared times modulus of 1 plus I. We know that the modulus of 1 minus I is the square root of 2, and the modulus of 1 plus I is also the square root of 2. Substituting these values, the equation becomes modulus of z times root 2 equals modulus of z squared times root 2. This simplifies to modulus of z squared minus modulus of z equals 0, which factors to modulus of z times the quantity modulus of z minus 1 equals 0. This gives us two possible cases. Either the modulus of z is 0 or the modulus of z is 1. Let's consider case 1. The modulus of z equals 0. If the modulus of a complex number is 0, the number itself must be 0. So, z equals 0 is one distinct root. Now for case 2, the modulus of z equals 1. If the modulus of z is 1, then the modulus of z squared is also 1. This means z times z bar equals 1, so z bar is equal to 1 over z. Let's substitute this back into our rearranged equation. We get 1 over z times the quantity 1 minus I equals z squared times the quantity 1 plus I. Solving for z cubed, we find it equals 1 minus I divided by 1 plus I. Simplifying the right side by rationalizing, we find that z cubed equals minus I. The equation z cubed equals minus I will have three distinct complex roots. So the total number of distinct roots is the sum of the roots from both cases. 1 root from case 1 plus 3 roots from case 2. Therefore, the total number of distinct roots is 1 plus 3, which equals 4. Let z be a complex number with a non-zero imaginary part. If the expression 2 plus 3z plus 4z squared divided by 2 minus 3z plus 4z squared is a real number, then find the value of the modulus of z squared. First, let's call the given expression w. We can write w equals 4z squared plus 3z plus 2 divided by 4z squared minus 3z plus 2. By adding and subtracting 6z in the numerator, we can split the fraction to get w equals 1 plus 6z divided by 4z squared minus 3z plus 2. Next, let's divide the numerator and the denominator of the fractional part by z. This gives w equals 1 plus 6 divided by 4z minus 3 plus 2 over z. The problem states that w is a real number. For w to be real, the denominator expression 4z minus 3 plus 2 over z must also be a real number. If that expression is real, then subtracting the real number 3 means 4z plus 2 over z must also be real. Dividing by the real number 2, we can conclude that 2z plus 1 over z is a real number. A key property of complex numbers is that a number is real if and only if it is equal to its own conjugate. So, 2z plus 1 over z must equal its conjugate. The conjugate of 2z plus 1 over z is 2z bar plus 1 over z bar. Let's rearrange the terms. This gives 2 times the quantity z minus z bar equals z minus z bar divided by z times z bar. Bringing everything to one side and factoring out z minus z bar, we get z minus z bar times the quantity 2 minus 1 over z bar equals 0. Recalling that z times z bar equals the modulus of z squared, our equation becomes z minus z bar times 2 minus 1 over modulus z squared equals 0. The problem states that z has a non-zero imaginary part, which means z is not equal to its conjugate. Therefore, the term z minus z bar is not equal to 0. Since the product of the two factors is 0, the second factor must be 0. So, 2 minus 1 over the modulus of z squared equals 0. Solving for the modulus of z squared, we find that 2 equals 1 over modulus z squared, which gives modulus z squared equals 1/2, or 0.5. Considering only the principal values of the inverse trigonometric functions, the value of 3 by 2 cos inverse of square root of 2 divided by 2 plus pi squared, plus 1 by 4 sine inverse of 2 root 2 pi divided by 2 plus pi squared, plus tan inverse of root 2 by pi is what? Let's call the given expression E. First, let's simplify the cos inverse term. We can write cos inverse of square root of 2 divided by 2 plus pi squared as tan inverse of pi by root 2 by considering a right-angled triangle. To do this, let theta equal cos inverse of the square root of 2 over 2 plus pi squared. This means cos theta is root 2 over the square root of 2 plus pi squared. In a right triangle, the adjacent side is root 2, and the hypotenuse is the square root of 2 plus pi squared. The opposite side will be the square root of the hypotenuse squared minus the adjacent squared, which simplifies to pi. Therefore, the cos inverse term is equal to tan inverse of pi over root 2. Next, let's simplify the sine inverse term. We will use the identity 2 tan inverse x equals sine inverse of 2x over 1 plus x squared. Let's substitute x as root 2 over pi. We find that the expression inside the sine inverse matches the formula. This means our sine inverse term is equal to 2 tan inverse of root 2 over pi. Now, let's substitute these simplified forms back into our original expression E. E becomes 3 by 2 times tan inverse of pi by root 2, plus 1 by 4 times 2 tan inverse of root 2 by pi, plus tan inverse of root 2 by pi. Simplifying, we get 3 by 2 tan inverse of pi by root 2, plus 1 by 2 tan inverse of root 2 by pi, plus tan inverse of root 2 by pi. Combining the like terms, we get 3 by 2 tan inverse of pi by root 2, plus 3 by 2 tan inverse of root 2 by pi. Factoring out 3 by 2, we have 3 by 2 times the sum of tan inverse of pi by root 2 and tan inverse of root 2 by pi. Now, we use the identity that tan inverse x plus tan inverse of 1 over x equals pi by 2 for any positive x. Applying this identity, the expression in the parenthesis becomes pi by 2. So, E is 3 by 2 times pi by 2, which equals 3 pi by 4. The numerical value of 3 pi by 4 is approximately 2.36, and that's our final answer.